The journey of an aluminum can begins with bauxite, the primary ore used to produce aluminum. Bauxite is formed through millions of years of weathering in tropical and subtropical regions. Unlike deep underground ores, bauxite is typically found close to the Earth's surface. This allows it to be extracted using open-pit mining methods. Bauxite is not pure aluminum. It is a mixture of aluminum-bearing minerals combined with iron oxides, silica, and other compounds. The concentration of aluminum within the ore determines how efficiently it can be processed. Low-quality ore requires more energy, more chemicals, and produces more waste. After extraction, the bauxite is loaded and prepared for transport. From here, the material begins a tightly controlled industrial process designed to separate aluminum from everything else. After leaving the mine, bauxite is transported to a refining facility. At this stage, the goal is no longer mining but chemical separation. The aluminum contained in bauxite is locked inside complex mineral compounds. It cannot be used in this form. To release it, the ore must be chemically processed into alumina. The refining process begins by crushing the bauxite into smaller particles. This increases surface area, allowing chemicals to react more efficiently. The crushed ore is then mixed with a hot sodium hydroxide solution. Under high temperature and pressure, aluminum-bearing minerals dissolve into the liquid. Iron oxides, silica, and other impurities do not dissolve. They remain solid and are separated from the solution. If this separation is incomplete, impurities will carry forward and weaken the final metal. The clear liquid is then cooled in a controlled process. As the temperature drops, pure alumina crystallizes out of the solution. These white alumina crystals are washed and dried to remove residual chemicals. The result is a fine powder containing a high concentration of aluminum. This material is now chemically prepared for metal production. The alumina produced during refining is not yet aluminum metal. At this stage, aluminum atoms are still bonded to oxygen. To separate them, chemical energy alone is not enough. Instead, the process requires a large and continuous supply of electricity. Alumina is transported to a smelting facility designed for electrolysis. Inside the smelter, alumina is fed into large electrolysis cells called reduction pots. Each pot is lined with carbon and filled with a molten electrolyte. When electric current passes through the cell, aluminum oxide breaks apart. Oxygen reacts with the carbon lining and is released as gas. Aluminum metal is freed and collects as a molten liquid at the bottom of the pot. This reaction only occurs at high temperature and constant electrical flow. If power is interrupted, the metal can solidify and damage the equipment. For this reason, smelting facilities operate continuously. Molten aluminum is periodically extracted and transferred for shaping. At this point, aluminum exists as a pure metal, ready for forming. Freshly extracted aluminum is still in liquid form. In this state, it cannot yet be shaped into cans. First, the metal must be cast into solid form. Molten aluminum is transported to casting equipment designed to control cooling. Here, the liquid metal is poured into wide molds to form large slabs. These slabs solidify as heat is carefully removed. Controlled cooling is critical. Once solidified, the aluminum slabs are transferred to rolling mills. Rolling is used instead of casting thin shapes directly. This allows thickness to be reduced gradually and precisely. The slabs pass through powerful rollers that compress the metal. With each pass, the aluminum becomes thinner, longer, and more uniform. Rolling also aligns the metal's internal grain structure. This improves strength while maintaining flexibility. Multiple rolling stages are required to reach the exact thickness needed for cans. If thickness varies, cans may fail during forming or pressurization. By the end of this process, aluminum exists as a continuous sheet. This sheet is optimized for strength, weight, and further shaping. The aluminum sheet produced during rolling is still flat. To become a can, it must be shaped into a hollow container. This shaping process is performed using a series of mechanical forming steps. First, the aluminum sheet is fed into a cupping press. Here, circular blanks are punched from the sheet. Each blank is then pushed into a shallow cup shape. This step establishes the base diameter of the can. Next, the cup enters the drawing and ironing process. During drawing, the cup is stretched deeper without tearing the metal. During ironing, the walls are thinned while the height increases. This controlled thinning reduces material use while maintaining strength. The bottom of the can remains thicker than the walls. This is intentional. The base must withstand internal pressure once the can is filled. If wall thickness is uneven, the can may wrinkle or collapse during forming. By the end of this stage, the can body has its final height and shape. After forming, the can body has its final shape but not its final finish. At this stage, the top edge of the can is uneven. This excess material must be removed. The can first passes through a trimming station. Here, the open end is cut to a precise and uniform height. Accurate trimming is essential. If the height varies, lids may not seal correctly later. Once trimmed, the can moves to the washing process. During forming, lubricants and metal residues remain on the surface. These contaminants must be completely removed. Washing uses a series of chemical baths and high-pressure rinses. Each stage is designed to clean without damaging the thin aluminum walls. After washing, the cans are dried using controlled hot air. At the end of this stage, the aluminum surface is clean, stable, and ready for coating. At this stage, the aluminum can is structurally complete. However, bare aluminum cannot safely hold beverages. Direct contact between liquid and metal would cause chemical reactions. These reactions could affect flavor and lead to corrosion. To prevent this, an internal protective coating is applied. This coating forms a thin barrier between the beverage and the aluminum. It must be uniform, flexible, and chemically stable. If the coating is too thin, the metal may corrode. If it is too thick, it can crack during can forming. The coating is sprayed inside the can at high speed. Excess material is removed to ensure consistency. The coated cans then pass through an oven. Heat cures the coating, locking it into place. Once protected internally, the can moves to external printing. Printing serves both functional and commercial purposes. It identifies the product, brand, and regulatory information. The ink must bond securely to the aluminum surface. If adhesion is poor, graphics may peel or fade. Printed cans are heated again to cure the ink. After cooling, the cans are ready for final shaping and inspection. At this stage, the can body is complete but not yet sealed. The open top must be reshaped to accept a lid. This process begins with necking. During necking, the diameter of the can is gradually reduced near the top. This allows a smaller lid to be used. Using a smaller lid reduces material cost and improves pressure resistance. Necking cannot be done in a single step. The aluminum is thinned and hardened from earlier forming. Reducing the diameter too quickly would cause wrinkles or cracks. For this reason, the can passes through multiple necking stages. Each stage reduces the diameter slightly. After necking, the rim of the can is shaped through flanging. Flanging bends the edge outward to create a flat sealing surface. This flange is critical. It must be uniform to form an airtight seal with the lid. If the flange is uneven, the can may leak or fail under pressure. Once necking and flanging are complete, the can has its final geometry. The body is now ready to be filled and sealed. Even after all forming steps are complete, the cans are not yet finished. At this stage, every can must be inspected. Small defects that pass earlier stages can still cause failure. Inspection systems check each can at high speed. Cameras examine shape, surface quality, and rim geometry. Sensors measure height, wall thickness, and roundness. Pressure and leak tests verify structural integrity. If any parameter falls outside tolerance, the can is rejected. Rejected cans are not wasted. They are crushed and returned to the recycling stream. This closed-loop process reduces material loss. Only cans that pass every inspection step move forward. Approved cans are grouped for packaging. They are stacked in precise patterns to prevent damage. Protective layers separate each level. The packaged cans are wrapped and secured. From here, logistics takes over. Cans are transported in large volumes to filling facilities. Factories are often located close to bottlers. This reduces transport cost and minimizes damage. At full speed, a single line can produce millions of cans per day. By the time this video ends, thousands more will have been completed.